Hey there, Chem Squad! This is the beginning of the fourth unit on chemical equilibrium. Alright, so just to recap some stuff from before, chemical equilibrium basically talks about a balance. And what is that balance? It's the rate of the forward reaction equaling the rate of the reverse reaction. Now, when this actually occurs, what happens to the concentration is that it will stay exactly the same. Okay, so you do not perceive a change in concentration. You actually don't even see anything happening. Equilibrium is dull. Okay, it's dull, dull, dull when it's actually occurring. So in order to achieve this state of dullness, okay, there are four conditions. Now, the first condition we kind of talked about in the previous class, but we'll kind of just re-examine the facts here. So, the first condition, rate of the forward reaction must equal the rate of the reverse reaction. So, let me give you an example, okay, and then afterwards I'll give you an analogy. So, in this example, we have copper sulfate. Now, it starts off as a solid on the reactant side, but when you look at the product side, it's been dissociated into its ions. So you have copper 2 plus ions, and you have SO4, which are the sulfate ions. Now, if we're talking about equilibrium, okay, we have to have the double arrows present, because the double arrows generally tell us that this reaction is reversible. That means we can go in both directions, forwards from reactants to products, or reverse from products to reactants. Okay, it all kind of just depends on how the arrows are kind of set up. So here, the top arrow is pointing towards the reactant side, so it's showing us the reverse reaction, and the bottom arrow is pointing towards the forward side, so it's showing us the forward reaction. So just to kind of be consistent with the arrows, okay, if we're talking about equilibrium, then the rate of the reverse, so rate of reverse, let's say it equals, I don't know, let's say 2.0 moles per minute. Okay, meaning that we're creating CuSO4 at 2.0 moles per minute. Well, in order for this to be a true equilibrium, the forward rate, so rate of the forward reaction, also has to be equal 2.0 moles per minute. So that if we are making copper sulfate from the ions, copper sulfate is breaking back down into those ions at exactly the same rate. Okay? If both of these are present and they're equal, then equilibrium has been achieved. And therefore, we don't really see anything changing, okay, when we look at the beaker. Because again, this change is pretty much equal. Whatever is happening to one side, it's automatically being undone to the other. Okay, so when we look at an analogy, a good analogy might be an escalator. So we'll draw an escalator here. And let's draw a person walking up this escalator. Yay, stickman! Okay, so the escalator is going down, the person is going up. In order for there to be equilibrium, okay, the person has to be traveling at the same rate as the escalator is going down. So let's say the rate of the person is 1 meter per second. Okay, so that's positive 1 meter per second. So he's going upwards. But the rate of the escalator is going down 1 meter per second, okay, or downwards. If this is true, if he's moving at 1 meter per second going up and the escalator is going 1 meter per second down, his actual position doesn't change. So the person on the escalator, oops, so person on the escalator does not change their position. He has not moved up or down. So basically, the displacement is still zero for all you physics people. But in terms of the rate, they're both equal. And they're both equal, you basically have an equilibrium, okay, a balance. So that's the first condition for any chemical reaction. You have to have equal forward rates and reverse rates. Condition number 2, a closed system. Okay? So key word is closed, but we've never talked about what system means. Okay? System in this case basically means a container where the reaction is occurring. Okay? A room, okay? A box. Wherever the reaction is happening, it's usually called the system. Okay? So we'll look at what an open system is like and what a closed system is like. So open system is kind of easy. So if we have, let's say, a beaker, okay, and let's say we have a substance inside the beaker. Let's say this is water. Water molecules can evaporate into a vapor, or it can condense back down into water. Okay, those are basically showing two opposing processes. But here's the problem. If this container is open, okay, it's not sealed off. So this is an open beaker. All those vapors will eventually escape. Okay? And very few would actually return back down to form liquid water again. So over time, the water evaporates. And you're basically left with less and less water. So in an open system, equilibrium is not reached. Okay? Because eventually you'll see a change. So the easiest way to fix an open system, okay, especially if it's a beaker filled with a fluid, is to put a cap or a lid on top. Oops. Okay. So if you put a lid or a cap on top, you've actually sealed off the environment so that anything that tries to escape cannot do so. Okay. So again, if this is water, okay, and you have molecules of vapor, okay, there's nowhere for it to go except to go back down, okay, and reform water. So here in this system, we see it being closed. It's closed off to the environment. So it's closed off to the environment. So that means we cannot pour anything into the system. We can't cause any sort of pressure changes, okay? Because anything that happens in terms of pressure only affects the outside, but it doesn't affect whatever is on the inside. So when we look at the word system, okay, system just means anything that is happening inside that container. So it equals the reaction inside the container. Okay. And sometimes people will also say that perhaps the container itself forms the system. Okay. Now, it's true that a lot of things cannot go in and out of a closed system. Okay. Open system, anything can affect the reaction, right? But a closed system, the only thing that can ever enter a closed system is actually heat. Okay, or more accurately, heat energy. So heat energy can pass through the walls, through the barrier of your system. Okay, so if it's really hot outside, energy can move in, and it's really cold outside, energy can move out of the system. Okay, but heat is basically the one thing that you can try to reduce. Okay, especially if you have a really well insulated bottle, but for the most part, you cannot stop it. Okay, the only way that you would ever have a constant environment that's basically not going to be affected by heat is when there is no heat at all. Okay, so when everything's at absolute zero, then you don't have to worry about heat energy passing in or out because there will be no heat energy at all. Okay, so let's move on to our third condition. Okay, third condition is called microscopic properties must be dynamic. Okay, meaning all the molecules and atoms must constantly be moving. So all atoms and molecules, which are normally microscopic, must constantly be moving. Okay. Of course, except when absolute zero is reached. But if you know your physics, it's pretty much impossible for absolute zero to be reached, because at that point you will have to destroy energy. Okay, you're breaking the rules of thermodynamics. So atoms and molecules must constantly be moving. Even though you can't see these molecules move, they are actually moving, right? So even when we look at solids, their molecules are still vibrating, even though the solid itself, when you look at it from the outside, it's just a solid sitting on a table, right? Nothing interesting. But if you can zoom in on the atoms and molecules, the atoms still vibrate. Okay? Or maybe there's still some kind of phase change happening that you cannot detect. Okay? So they can still vibrate or move about. Okay? It's limited, but there's still motion. Okay? And that's the key. At the microscopic level, there must still be some kind of motion happening between your atoms and molecules. So that means when we zoom out and we look at things at the macroscopic level, okay, macroscopic properties are things that you can measure. Okay, they're properties that you can measure and see. These kinds of properties have to be constant, which means that it's unchanging. Okay, so to give you several examples, some things that are macroscopic could be things like color. Okay, you can measure color, okay, by measuring its intensity, how dark or light it is, and you can also measure if it's changing or not. See? So for color, color cannot change. So it won't change during equilibrium. Okay. When it's not at equilibrium, yeah, there's color changes everywhere. So not at equilibrium, color changes occur. Okay. So let's give you a list of common macroscopic properties. Okay. So color is one of them. There's also mass, volume. You can also measure shape, density. Okay, all observable, okay, or detectable changes. So things like odor or smell. Okay, light intensity. Okay, these are all things that are considered to be macroscopic. Okay, and there's probably a lot more if we just sat down and thought about it. But as long as you can measure them, okay, as long as it's detectable and measurable, they are considered to be macroscopic properties. Okay. So as long as these four properties or four conditions are present, we will have equilibrium being present. Okay. Now, there's one last thing that I'm going to add to all of this. And it's a big note. Most of the time in the lab, okay, we typically don't run labs in a closed environment. Okay, I mean, the room that we're in might be closed, but the actual reaction where it's taking place, it's often not closed. It's often open. Okay, so if all conditions are met except the system is open, then we have a reaction occurring at what we call steady state. Okay. Steady state is not equilibrium. It's close, but it's technically not. Okay. You can think of it as equilibrium in an open system. Okay, but more commonly we just call it steady state. we kind of recognize that during a lab, even in an open system, as long as the temperature doesn't change too much and we're not doing something foolish by adding something into our system that shouldn't be there, most of our data should basically be pretty accurate. Okay, almost just as accurate as if you were in a closed system and actually measuring equilibrium. Okay, so that's the one tiny note here. So steady state, okay, is a thing. We in the lab basically operate at steady state and not exactly at equilibrium. All right, so those are the 4 conditions. I gotta go. My wife is waiting for me, so I'll see you guys next time. Take care.